So, good evening, everyone, and welcome to today's lecture. Everyone seems to be chilling out, so that's good. So, let us now move on to our discussion. And what we were discussing in the previous class, we were discussing
Gravitation.
gravitational potential, and we had done some problems on gravitational potential. We had seen the gravitational potential because of different types of masses, a ring, a spherical shell, and most importantly, the sphere. And we had seen how we can solve questions based on this. Yes or no? No, yes.
Yes, sir.
Do we remember this? We
We
found
remember.
out the various questions we had done. Okay, just to refresh our memories, I will give you one question that I was supposed to give in the previous class, but then I could not give it. I can't give this question because this is not there. Just give me a minute. I will find out that question and I will give it if I can find it out. Not able to find out. That's the problem. If I can't find it out, I will have to draw it on my own, which I don't want to do. Just because other drawings are always better than mine. I always like to take the drawing from there and then move ahead. I will draw only when it's absolutely necessary for me to draw. Let me see if I can get a drawing. Let me see if I can get a drawing from here. Okay, I can probably do with this drawing. I'll have to do with this drawing, nothing else. I'm not getting anything. So, what I have is a ring of radius A. I have a ring of radius A, and this ring has a mass M, capital M. Let me just take this out. A ring has a mass capital M and radius A. Then, at a very large distance, there is a small mass kept at rest at infinity. This is fixed. This is not going to move. This is fixed and this is not going to move. So, what is going to happen with this small body of mass M? What will happen to this small body of mass M? It is going to move towards this. When it reaches the center of this ring, you have to find out what is the velocity of this body when it reaches the center of the ring. So, I hope you can understand this question from where it is coming, right? So, this is just a continuation of what we were doing in the previous class. This is just to find out whether you understand it or not. So, I'll give you 2 minutes to give me the answer for this one. I hope you can do this. So I will do it. How I'm going to do it? I'm going to call this point as A, and this point is infinity. I'm going to apply work energy theorem from infinity to point A. Work done by all forces from infinity to A, and the only force acting here is gravity. So work done from infinity to A by gravity shall be equal to change in kinetic energy. Now, how do I find the work done from infinity to A by gravity? I multiply the mass by potential at infinity minus potential at point A. That should be equal to change in kinetic energy, half mv square minus 0. M and M goes away. What is the potential at infinity? It is 0. Potential at point A, which is the center of this, is minus gm by A. Minus of minus gm by A becomes gm by A. Gm by A is equal to half into V square. So your V becomes under root of 2 gm by A, and that is the answer that we were looking at. That is the answer that we were looking at. Everyone got this? Yes or no? Anyone got this answer?
We got it, sir.
How many of you got this answer? No one. Okay. No one got this answer? Anyways, the next heading is gravitational potential energy. Now, from gravitational potential, we jump on to gravitational potential energy. And actually, it is not gravitational potential energy, but it is gravitational potential energy change or gravitational potential energy difference, because absolute value of gravitational potential energy is not defined. So that is the first thing that you must understand. Absolute value of gravitational potential energy is not defined. Then what is defined? What is defined is the change in gravitational potential. So change in delta, change in gravitational potential energy in moving from a point A to point B is negative of work done by the gravity. Do we understand this? It's negative of work done by gravity. And now you know that will be equal to negative of work done by gravity, that will be equal to m into Va minus Vb. Sorry, it will be equal to, just write it here like this. Do we understand this? Yes or no?
Yes, sir.
Now, this negative of work done divided by mass gives you the change in electrostatic potential. So all these three things are related to each other. How are these three things related to each other? So you can write UA minus UB will be equal to work done by gravity from A to B. Do you remember how I've written this? And I told you to remember this, yes or no? That will be equal to m times Va minus Vb. So this is the relation between the three quantities. Now, if the potential energy at infinity is taken as 0, then we can define the energy at any point. The energy at any point will be equal to minus the negative of work done. Do we understand this?
Yes, sir.
If we have, so it will be negative of work done in that case. So that is how we define it. Do we get this? Yes or no?
Yes.
So always the absolute value is not defined. It's only change is defined. I'll give you a minute to know. Okay. Now, if we take the potential energy at infinity to be 0, we can define the potential energy of any point. Now, the first thing that we are going to do is we are going to understand gravitational potential energy. I call it GPE of a system of two charges. Gravitational potential energy for a system of two charges. Now, if I have two charges, M1 and M2, separated by a distance of r. Remember, gravitational potential energy is always negative, and I am taking the energy when they are at infinite distance apart as 0. Then the gravitational potential energy in this case will be given by minus G into M1 divided by R. How I found it out? I found out the potential due to one charge, and I multiplied it by the second charge. The potential due to one charge will be minus gm1 by r, and I've just multiplied it by m2. Or I have found out the potential due to mass m2 minus gm2 by r and multiplied it by m1. Do we understand this? This is how we find the gravitational potential energy of a system of two charges. Now, if you have more than two charges, how will you find the gravitational potential energy of that system? So I'll give you a question, and based on that question, you can tell me what will be the gravitational potential energy of this system. We will be doing more questions on this. Don't worry. The right now, just let us concentrate on simple question. M, and M. These are four masses, and they are placed on the corners of a square of edge length A. What we have to find out? You have to find out the gravitational potential energy of this system. I'll give you 2 minutes to tell me how will you find out the gravitational potential energy of this system. Remember, we only know gravitational potential energy of 2-point charges. From that 2-point charges, how are you going to find the gravitational potential energy of 4-point charges? I will give you 2 minutes to think about it and then give me the answer. Well, I think I've given you enough time to think how are you going to solve this? How are you going to solve this? You only know the potential energy of a two mass system. What you are going to do, you are going to find out how many pairs are there. This is pair number 1, pair number 2, pair number 3, and pair number 4. Every pair has energy minus G into M1 into M2 by A. So the 4 pair becomes minus 4 G M square by A. Do we understand this?
Yes, sir.
Then I have one pair, the fifth pair like this, and then I have the sixth pair like this. So basically, when you have more than 2-point charges, how do you find the energy of the system? You find pairs. So now the energy of this pair minus 2 gm square by root 2a. Why I multiplied it by 2? Because there are two pairs of m and m whose distance between them is root 2a. Do we understand this? Yes or no? Yes or no?
Sir.
Okay. That is how you are supposed to do this. You will hardly find any questions on this, because in this chapter on gravitation, we are mostly concerned with not the gravitational potential energy of a 2-point mass system, but the gravitational potential energy of a big planet and a small mass. Now, you can also find the gravitational potential energy of a big planet and a small mass based on the same concept. How will you find out the gravitational potential energy of a big planet and a point mass? The big planet and a point mass. So you can now write this gravitational potential energy of a sphere, or gravitational potential energy of a planet and a small point mass m. How will you find it out? Yes, these are the type of question that we are most likely to encounter. So you will have a big planet, and most of the time it is going to be Earth. The mass of the Earth or the planet will be given as capital M, and the radius may be given as r or re. And then you will have some body, some small point mass m placed at a distance r, and this r would be from the center of the planet. Do we understand this? Yes or no? So the shortcut way of finding out this potential energy is, this is a sphere. You can find out the potential at the point A. What is the potential at the point A? What is the potential at the point B? The potential at the point B will be minus G into capital M by small r. Yes or no? You just multiply that potential by the mass. So you will get the potential energy of this system as minus gmm by r when this body is placed at the point B. Do we understand this? Where r is the distance from the center of the planet. When this body is placed at point A on the surface of the planet, the energy becomes minus gmm by capital R, where capital R is the radius of the planet. Are we able to understand this, or this is going above or it's saying bye bye? When this object is placed at infinity, the gravitational potential energy, the mutual gravitational potential energy becomes zero. Do we understand this? Yes or no? So this is how you can find it out. You can find out the gravitational potential energy of a planet and a small mass m. Everybody understands this? Yes or no? Okay. Now the next thing that you understand, as soon as you understand the gravitational potential energy of a planet and a point mass, the next thing that we are going to understand is the escape velocity. Escape velocity from a planet. Now, what do you mean by escape velocity from a planet? Anyone has any idea what is escape velocity from a planet? What do you mean by escape velocity from a planet? You will have a planet of mass m and radius r. You will have a planet of mass m and radius r. What do you mean by escape velocity from the planet? Yes, tell me, tell me. Yes, what do you mean by escape velocity?
Sir, the minimum energy required.
Minimum
Sorry,
energy.
minimum velocity.
So
Minimum
what you are
velocity.
going to do is you will have a small body of mass m on the surface of this planet, and you are going to project it with a velocity v. What is the minimum velocity I must give so that it escapes the gravitational pull of earth and goes to infinity? Do we understand this? Yes or no? That v minimum is known as v escape or ve or vesp, v escape velocity. Now, how do you find out this escape velocity? This point is a, this point is infinity. I can do this question in two ways. What are the two ways in which I can do this question? I will tell you all the two ways, and then we will choose one way. What are the two ways in which you can do this question? You can apply work energy theorem, the mother theorem, from a to infinity. What does this mother theorem say? Work done by all forces, or work done by all forces. Here only one force is acting, from a to infinity, by gravity, is equal to change in kinetic energy. What is the work done by this gravitational force? So this will be m into potential at point A minus potential at point B. That should be equal to change in kinetic energy. The final kinetic energy at infinity will be 0, and the initial kinetic energy will be half mv square. Do we understand this?
Yes, sir.
Potential at point B, which is infinity. Let me write infinity. Potential at infinity is 0. Potential at point B is minus gm by r. So it becomes 2 times gm by r ka under root becomes your v escape. Do we understand this? Yes or no?
Yes, sir.
V escape velocity becomes root over 2 gm by r. Now the same question I could have done it in a different way. How could I have done it in a different way? I could have, since there is only gravity acting, I could have applied Lockme from a to b, a to infinity in fact. If I would have applied Lockme from a to infinity, total mechanical energy at point A shall be equal to total mechanical energy at point B. Yes or no?
Yes, sir.
Now, the kinetic energy at point A is half mv square. Potential energy at point A is minus gmm by r. That must be equal to total energy at the infinity point is 0. From here also you can get the same concept 2 times gm by r. Do we understand this? Yes or
Yes.
no?
Yes, sir.
So this is how you can find out the escape velocity from the planet in this way. Do we understand this? Now, whether I throw it like this or whether I throw it from here like this, the question remains same. Yes or no? Yes or no? From here, if I throw it and it reaches infinity, the same question is here. Yes or no?
Yes, sir.
So I throw it anyways, perpendicular to the surface of the earth. The question remains same. Now, this question should have reminded you of something that we have already done. Did it remind you of something that we had already done?
Mm.
We'd already done a question in the last class where
Yes.
instead of giving the question how much should I put it here, I put the question in a different way. An object is at infinity. With what velocity it strikes the surface of the planet? This is the brother of this question.
Yes, sir.
This is the brother of this question. Do we understand this?
Yes, sir.
So remember this. Both the questions are similar. So even that question could have been done. Even that question could have been done with the same concept. Instead of applying work energy theorem, I could have applied the law of conservation of mechanical energy. Do we understand this? Yes or no? No,
Yes,
yes.
sir.
Okay, now please remember these factors. On what all factors this escape velocity depends on? This escape velocity from a planet depends on the mass m and radius r of the planet and the position from where the object is projected. If it is projected from surface, it will be same. But if it is projected from somewhere else, it may be different, because we have seen that if we project it from the center of Earth, the speed will be different. Do we understand this? Yes or no?
Yes, sir.
Yes or no? Do we understand this? Now, on what all factors it does not depend on? So the escape speed does not depend on the mass of the body which is projected. It also does not depend on the angle of projection. So escape velocity does not depend on these quantities. I'll give you 2 minutes to note it down. So the escape velocity from Earth, if you put the values for Earth, we escape from Earth is 11.2 kilometers per second. That is the escape velocity from the planet Earth.
Yes.
Now, you can remember these formulae for escape velocity in different ways, because there are a lot of times where this question has come on escape velocity, how it depends on. So the first formula is already we have seen, root over 2 gm by r. That is the first formula. We remember this.
Yes,
So it
sir.
is directly proportional to the mass and inversely proportional to what? The radius of the planet. Yes or no?
Yes, sir.
The second way in which you can write the same formula is, and the more number of ways you can remember, it's better, root over 2 gr, where g is the acceleration due to gravity on the surface of the planet. I hope you understand this.
Yes, sir.
Gm by r square is written as small g, and that is how I'll end up with this formula. The third way in which you can write the same thing is this. This is in terms of your radius and your density of the planet. You must remember all these three different ways, because a question may come based on any of these quantities. Do we understand this?
Yes, sir.
Now, if a body is projected with a velocity equal to the escape velocity, it will escape the gravitational pull of Earth and it will never come back. If it is projected with a velocity which is less than the escape velocity, Then what will happen? It will go to a certain height and then it will fall back. Yes or no? If it is projected with more than the escape velocity, it will go to infinity and it will have some energy left in it as well. So, are we ready to solve some questions on this? Okay, let me find out this one. So just to make you understand, that question can come in any way. So this is the question. The escape velocity from Earth is about 11 kilometer per second. The escape velocity from a planet twice the radius and the same mean density will be how much? Question number 1. So you just have to remember.
A, sir.
Yes?
A, sir. 22 kilometer per second.
A, sir, everyone understand this, sir?
Yes, sir.
Pakka?
Paka, sir.
Okay, great. 22 kilometer per second. Well done. Good. This is just to make you understand the types of question that can come. Here comes the next one. And again, in your exam, if you are lucky, you same question may land up. This is question number 2. A projectile is projected with a velocity k times ve in vertically upward direction from ground into space. V is the escape velocity and k is less than 1. So it is not more than escape velocity, it is less than the escape velocity. What, up till what height will it go? I'll give you 2 minutes to do this. How I'm supposed to solve this? It is a pretty straightforward question. This is your planet and you project it from this point, point A. Your velocity of projection is k times ve. That's it. So it will go up till certain point. Let me call this point as B and let me call the distance of this point from the center of Earth as small r. The radius of the Earth is given as capital R. I will just apply lockme from point A to point B. Mechanical energy at point A should be equal to mechanical energy at point B. The kinetic energy at point A is half m into v square. V square is k square into ve square plus the potential energy at point A is minus gmm by r. That must be equal to kinetic energy at point B. It is not going to go any further, so kinetic energy is 0 minus gmm by small r. Now you must know that the value of escape velocity is 2 times gm by r root. So I will just put that value 2 times m. I don't have to write m here because m is going to get cancelled, cancelled, cancelled. So half into k square into gm, sorry, 2 gm by r minus gm by r. That will be equal to minus gm by small r. Gm goes, this goes, this goes. From here you should be able to calculate the value of r, and the value of r that I think that you are going to get will be capital R divided by 1 minus k square. That is the answer, bachcho, that I was looking for. Now please tell me what was the problem in solving this? What you could not understand? Yes? What was the doubt? No doubt, but we could not solve it. Anyways, it can happen that you don't have any doubt, but you are not able to solve it. So there was no doubt, and we were not able to solve it, right? Okay. Anyways, this is the next question that I have. I think we did this question before also. I don't know. A very small groove is made in the earth and the particle of mass m0 it placed at a distance r by 2 from the center. Find the escape velocity of the particle from that place. From which place? At a distance of r by 2 from the center of earth. I'll give you 2 minutes to solve this. So I'm going to leave this question for you as an homework because there is no point of me solving it and you not paying attention at all. So how you got to do this? You already have all the
Sir,
items
is
and
it under
utensils
root
to
GM
solve
by
it,
R?
but still you are not able to do this. That means there is something wrong and you need to look at all the
Sir,
formulae.
sir,
Yes,
under root GM by R.
it's not under root gm by r, it's not under root 2 gm by r, it's not under root 4 gm by r, 6, 8, 7, 9, 10, nothing like that. So you will have to think about it, and you have time now till tomorrow. Tomorrow 9 o'clock we are meeting again, I think so, and we'll have the class. And I was supposed to end your gravitation in tomorrow's class. Let's see if I can do that. It looks improbable, but I will try to do it. And if you help me out by giving me the answer of this question, it would really help. So I will hope, against hope, that I will get an answer to this question. And how are you going to solve this question? Whenever I give you a question, there is nothing in that question that you don't know that is required to solve this question. Then only I give you a question. So I've told you everything that you needed to know, and I hope that you can do it. So
Sure,
I
sir.
will wait till tomorrow. Take care. God bless all of you.
Thank you, sir.
Bye, everyone.